Okay, so we're going to look at equations in quadratic form. So in our previous classes, we looked at how to solve polynomial equations, radical equations, rational exponent equations. Today we're going to continue our work with some more special categories. Okay. The first one being equations that are in quadratic form. Okay. So in each of these three examples, if I introduce a new variable, so this is going to seem a little out of the blue, right? But in this first one, if you let u be x squared, so everywhere you see an x squared in this equation, we're going to replace it with a u. How would I rewrite x to the fourth with a u instead? U squared. Good. So this is going to become u squared minus 10, and instead of x squared, I'm going to write a u, plus 9 equals 0. And that guy written in blue, u squared minus 10u plus 9 equals 0. Do you know how to solve that? Yeah, factor or quadratic formula, right? So if I wanted to make this second one look like a standard quadratic formula, what would I choose for u? X plus 3. Wherever I see an x plus 3, I'm going to put a u instead, and this is going to become u squared plus 7u minus 18 equals 0. Now it's just a plain old quadratic equation. This last one's a little trickier. Any ideas? X to the 1/3, yeah. So x to the 2/3 is x to the 1/3 squared, so this becomes 5u squared, plus x to the 1/3, so this is 11u plus 2 equals 0. So this type of equation, yeah, I just threw a u in. I just decided I'm going to introduce a new variable that's going to make this look like something I know how to solve, right? We're going to throw the water on the floor. Make it look like something you know how to solve. So, but to do that, I introduce a new variable. Okay. So let's actually go through the whole process with a specific problem. So I have x to the 4th minus 10x squared plus 9 equals 0. So we're going to let u equal x squared. So I'm going to have u squared minus 10u plus 9 equals 0. Right? Because x squared squared is x to the 4th. So that means u squared. X squared is u. All right, so now I want to solve this quadratic equation. So one of my sides is already 0. So I want to see if I can factor it, or I could use a quadratic formula, but does this factor? Yeah, this factors to u minus 1, u minus 9. Set each factor to 0. Okay, so then I solve each one and I get u equals 1 or u equals 9, but I am not done. Why am I not done? U is x squared. Yeah, there were no u's in the original problem. So I've solved for u, but the problem asked me to solve for x. So now replace my u's with x squareds, right? Because u equals x squared from my first step up here. Let u equal x squared. So instead of u equals 1, I write x squared equals 1. And instead of u equals 9, I write x squared equals 9. And then I solve each of these. So if x squared equals 1, what does x equal? Plus or minus 1. And if x squared is 9, x equals plus or minus 3. What do you think? All right, so what if I wanted to solve x plus 3 squared plus 7 times x plus 3 minus 18 equals 0? What should we let u equal? X plus 3. Okay. Rewrite the equation and solve it. So we get u squared plus 7u minus 18 equals 0. Does that factor? Yeah, 9 and 2 should work. So x plus 9, x minus 2. Oops, sorry, those are u's. That's important. So then u plus 9 equals 0, or u minus 2 equals 0, u equals negative 9, or u equals 2. But I am not done. I have to go replace my u's with what? X plus 3 this time. Replace u with what you let it equal at the beginning. So we have x plus 3 equals negative 9, or x plus 3 equals 2. So x equals negative 12, or x equals negative 1. I'm going to have you try the last one on your own. I will just give you the hint that you're going to let u be x to the 1/3. And you can go from there. Okay, so my hint was let u equal x to the 1/3. And the whole purpose of doing that is that now I can replace, every time there's an x to the 1/3 in my equation, I can replace it with a u. So this is going to simplify things. So start with x to the 2/3. X to the 2/3 is the same thing as x to the 1/3 squared. Because when you raise a power to a power, what do you do with the two exponents? Multiply. Yeah. So if I have x to the 1/3 squared, 1/3 times 2 is actually 2/3. So instead of writing x to the 1/3 squared, I can now write u squared. So I can replace x to the 2/3 with u squared. So this becomes 5u squared plus 11. I have an x to the 1/3, so that's a u, plus 2 equals 0. Does this thing factor? It does. Sometimes when the coefficient is not 1, factoring can be more time consuming because you have to do more guess and check. So if you spend more than a minute, maybe you just give up and go to the quadratic formula. Right. So that would be u equals negative 11 plus or minus the square root of 11 squared, which is 121, minus 4 times 5 times 2, all over 2 times 5. This is negative b plus or minus the square root of b squared minus 4 times a times c, all over 2a. Funny. So this becomes negative 11 plus or minus 9 over 10. Okay, so negative 11 plus 9 is negative 2 over 10 is negative 1/5. And negative 11 minus 9 is negative 20 over 10 is negative 2. So those are my two values for u. Okay, so I've got u equals negative 1/5, u equals negative 2. But I wasn't asked to solve for u, I was asked to solve for x. So I have to translate back, right? So I made a translation to start. I replaced all my x to the 1/3 with u's. Now I have to do it again. I have to go back to x's. I have to replace u's with what? X to the 1/3. Each u I have here, I'm going to replace with an x to the 1/3. Instead of u, I write x to the 1/3. Because u and x to the 1/3 are equal, so I can make substitutions with those two. How do you solve something to the 1/3 equals a number? Cube it. Yeah. I'm going to raise both sides to the 3rd power because when you raise a power to a power, you multiply the exponents, and 1/3 times 3 is 1. So this is just x to the 1st or x. And when I cube a negative 1, I get negative 1. Cube 5, you get 125. Same thing with this one. Cube both sides. X to the 1/3 cubed is x. Negative 2 cubed is negative 8. Now, Gabby, I think you got 0.008 for this. Same thing. Type in 1 over 125 in your calculator and you'll get that decimal. All right. We ready? to move on? Okay. All right, now we're going to look at equations with absolute values in them. How to solve an equation with an absolute value in it. So we're going to use a graph to solve the absolute value of x equals 3. By typing the absolute value of x, I'm going to graph the absolute value of x, and I'm going to graph y equals 3. I'll actually do it in GeoGebra just because it's a nicer picture. Okay, so I graphed the absolute value of x by typing ABS parentheses x. And then the other side of my equation is going to be 3, right? Because I'm trying to solve when does the absolute value of x equal 3. So I'm graphing absolute value of x, and then I got to graph 3 as well. So I'm going to graph y equals 3. And then what is the solution to the equation? How does this graph help me answer the question? The intersection, yeah. So I'm going to do intersect, square bracket, f of x, comma a. And it only does one. This is so weird. That happened to me yesterday too. So it only gave me 1, which is at negative 3, 3. Can you read what this one is right off the graph? 3, 3. It might help if I show the grid. There we go. So now this one's at negative 3, 3. This one's at 3, 3. So what are actually the solutions? Negative 3 and 3. It's the x coordinate of those points. So x equals positive 3 or negative 3. Does that make sense that those are the only two solutions to absolute value of x equals 3? Yeah, I mean, if you're talking about what numbers have an absolute value of 3, well, the absolute value of 3 is 3, and the absolute value of negative 3 is 3. So this is we're gonna be able to generalize this to a absolute value of anything, not just a plain old x, right? Generalize this observation for all absolute value equations. If you have the absolute value of some stuff equal to c, you can set your stuff equal to c or to negative c. So yeah, for example, let's look at the absolute value of 2x plus 1 equals 11. So first, we rewrite this without the absolute values, and you translate this into two equations. If the absolute value of this stuff is 11, that means the value of that stuff could be 11, or what else could it be? Negative 11. Yeah, because the absolute value of that stuff is 11. So whatever's in there could be 11 or it could be negative 11. Either way, the absolute value of it would be 11. So then I solve both of these equations, just the usual way. So I end up with x equals 5 or x equals negative 6. And then we should just do a quick check, right? Plug a 5 in here. Absolute value of 2 times 5 plus 1. 2 times 5 is 10, plus 1 is 11. The absolute value of 11 is 11. And then plug in a negative 6. 2 times negative 6. Oops. 2 times negative 6 plus 1. 2 times negative 6 is negative 12. Negative 12 plus 1 is negative 11. And the absolute value of negative 11 is 11. Yeah.
Okay. So really quick thing, I was wondering, would this graph here, like for absolute value graphs, like 2x plus 1,
Mm-hmm.
so like when it was x or whatever, it was like, it just went up like y equals x, like
Yeah.
on one side.
Mm-hmm.
And if it was, so let's say 2x plus 1, it would go up like 2x, like,
Yeah.
it was like, it's like whatever in the absolute value is like the,
That's going to be like the right-hand side of the graph. Yeah, let's take a look at the graph of the absolute value of 2x plus 1. Absolute value of 2x plus 1. So it looks like this. Make it a different color so you can tell the difference. Okay, so it's this red graph, and the right-hand side of this graph, well, just what you were describing, has a slope of 2 and a y-intercept of 1. That's the line 2x plus 1. And then if I were to just continue that line, like let's just graph plain old y equals 2x plus 1, no absolute values. It just continues down, right? So it's just this whole line. When I take the absolute value, you take all the negative y values and you just reflect them up and make them positive. So this guy down here gets reflected over the x-axis. This is like a mirror, and it just makes them all positive. All right, let's do one more together. If I want to solve 3 times the absolute value of 2x minus 1 plus 4 equals 25, I know how to solve the absolute value of some stuff equals a number. So let's make it look like that, right? We'll dump the water on the floor. Isolate the absolute value. So I'm going to move the 4 over, and I get 3 absolute value 2x minus 1 equals 21. Divide by 3, so I have the absolute value of 2x minus 1 equals 7. Now translate it to 2 different equations. So what are my 2 equations? Very close. What did he say that he shouldn't have said? Don't say the absolute value. Once you translate it to 2 equations, that's how we get rid of the absolute value bars. So either 2x minus 1 is 7, or 2x minus 1 is negative 7. Either way, the absolute value of 2x minus 1 will be 7. And then you just solve each of these. So here we get x equals 4, and here we get x equals negative 3. All right, take a couple of minutes and think about this next equation. It has no solution. Think about why not. Okay, so if I try to follow the method that I just taught you, right? The first thing we would do is try to isolate the absolute value term. So I'll subtract 4 from both sides, and I get the absolute value of x equals negative 2. Before you do any more work, you should immediately go, oh, there's no solutions. Why not? Yes? Yeah, the absolute value of something can never be negative. There is no number that when you take the absolute value of it, you get negative 2. The absolute value of everything is either positive or 0. So this is not possible. The absolute value cannot be negative, right? If I ask you what's the absolute value of anything, whatever number I say, the answer is always positive or 0, right? It can never be negative 2. Never be negative. What would this thing look like graphically if I tried to graph absolute value of x and negative 2? What would it look like? Absolute value of x, we saw that picture already. It looks like this, right? This is y equals absolute value of x. What does y equals negative 2 look like? Horizontal line at negative 2. This is the line y equals negative 2. And what can you say about the intersection of these 2 graphs? They never cross, which means there are no solutions to the equation absolute of x equals negative 2. All right, last topic for today, linear inequalities. If I wanted to represent all of the numbers x that are less than or equal to 7, how would I do it on a number line? Anybody done this before?
Yeah, open circle, like open circle if it's less than, closed circle.
Yes. Closed circle if it's or equal to. So this says all the numbers that are less than or equal to 7. So we're including 7 in the set. So I would put a closed circle on 7 and then shade everything below 7. Some texts, and I believe I can't remember if our book is one of them, instead of using a closed circle and an open circle, they use a square bracket for including the 7, and a round bracket for not including. So for people who have done this before, closed dot is the same thing as square bracket. Open circle is going to be the same thing as round bracket. No. These are supposed to be arrows. Those are very unclear. Square bracket. Right. Right. So I can graph this thing, or I can use set builder notation, which we learned earlier in the semester. We could say, oh, this is the set of all x's such that x is less than or equal to 7. And we have another, perhaps more convenient way to represent solution sets called interval notation. So this notation right here, round bracket, negative infinity, comma 7, square bracket, that means all the numbers less than or equal to 7. You read it, you always write smallest to biggest, left to right. So the smallest number in this set, there is no smallest number, so you go all the way down to negative infinity. And then the biggest number in the set is 7. You can't get to infinity, so you use a round bracket to indicate not included. And we include the 7, so you use a square bracket. So some examples of closed, open, and infinite intervals are here. So if I wanted to graph this square bracket, 2, 3 square bracket, that means all the x's between 2 and 3, including the 2 and including the 3. So I would graph that like this. Include the 2, include the 3, shade everything in between. Square brackets mean include the endpoints. Yeah, that's it. -1, 5 with parentheses rather than square brackets means all the x's between -1 and 5, not including the -1 or the 5. So I put open circle, shade. Right. Or alternatively, some people would put parenthesis, shade. It's okay to do it either way. Yep, that would be fine. The advantage to using the square bracket and round bracket on the number line is it's the same notation as the interval notation, so you don't really have to like translate. So parentheses indicate that the endpoints are not included. You could have one endpoint included and not the other, like -4, 1. We're not including the -4. We are including the 1, and you just shade all the numbers in between. Alternatively, open circle, closed circle, shade. When you're talking about infinity all the way to the left, you use a negative infinity. All the way to the right, you use positive infinity. We always use parentheses on infinities because you can't get there, which means it's not in the set. Okay, so this is just some notation that's going to help us answer linear inequality problems. Okay, so linear inequalities can be solved just like linear equations. You just do the exact same stuff that you already know how to do with one notable rule change. So see if we can figure out what this rule change is by solving and checking these two problems. All right, so 3x plus 3 is bigger than or equal to 0. I just want to solve this thing for x. Pretend there's an equal sign there and just do everything you would normally do. So I have 3x is bigger than or equal to -3, x bigger than or equal to -1. And then we should check. Pick one number from the set of numbers that's bigger than or equal to -1. Any number bigger. 1, 4, any number. Yeah. Let's plug a 4 in. 3 times 4 is 12, plus 3 is 15. Is that bigger than 0? Yeah, so we trust our solution set here. If I want to graph it, bigger than or equal to -1, put a square bracket, shade to the right. In set builder notation, I would say the set of all x's such that x is bigger than or equal to 1, -1. And in interval notation, I would put -1, comma, infinity. Include the -1, but not the infinity. Does that make sense? All right, let's do the same thing for b. Just follow our standard procedures. I'm going to divide both sides by -4. So I get x is less than -2. So let's check our solution set. Pick any number smaller than -2. -5. -4 times -5 is +20. Is 20 less than 8? No, so something messed up here. Let's pick another number, any number smaller than -2. -1. -4 times -1 is 4. Is 4, sorry, -1 is not smaller than -2. 1 is bigger. We just did -5. -7, okay. -4 times -7 is +28. Is 28 less than 8? No. When we accidentally just checked -1, it was true though, right? Yeah, we got 4 is less than 8. So if we turn this around, if you switch the less than and make it a greater than, does that work? Any number bigger than -2. Give me one. 1. -4 times 1 is -4. Is that less than 8? Yeah. So this works. So we had to turn the alligator around. Anytime you multiply or divide by a negative, when solving an inequality, that's when the alligator turns around. So that's our one little rule change, the one little difference between solving an equation versus an inequality. Multiply or divide by a negative, and the inequality reverses. I always think of this as the alligator turns around. Right? My inequalities are like alligators. They always eat the bigger number. So the alligator turns around. No, not on the equal. Well, when it's equal, when you turn an equal sign around, it's exactly this. Oh, you mean if it was less than or equal to? Yeah, same rule applies. Yep. All right, so let's, now that we know the solution set is x is bigger than -2, let's graph it and write it in interval notation. Actually, why don't you do that, and then we'll go over it. Okay, so let's graph it together. X bigger than -2. So I'm not including the -2 here because it's not or equal to. So I just put an open circle on -2. And then which side do I shade to indicate bigger than -2? To the right. So if I want to put that in set builder notation, it's just the set of all x's such that x is bigger than -2. In interval notation, what's the smallest number in this set? -2, well, not quite because we don't include it, right? But so you do parenthesis -2. And then what's the biggest number in this set? Infinity. We never include the infinities, so -2 to infinity. All right. What do you think? Any questions? All right. When we have a linear inequality that contains fractions, look at these two linear inequalities. Which one would you rather solve? The one on the left or the one on the right? The one on the right, because it has no fractions. We learned several classes ago how to get rid of fractions. When you're solving an equation, what do? Multiply both sides by the least common denominator. So I multiply the left side of this guy by, what's my least common denominator of 2, 3, and 6? 6. So multiply this guy by 6. Multiply this guy by 6. So, and you can think of this as 6 over 1, if that helps you. 6 over 2, what does that reduce to? 3. So this is going to be 3 times x minus 4, greater than or equal to. What is 6 over 3 reduced to? 2. So I'm going to have 2 times x minus 2. And then what's 6 over 6 reduced to? 1. So I just have the 5 left in the numerator. 6's cancel. So these two inequalities are actually equivalent. They have the same set of solutions. And then we solve this guy. So distribute my 3, I get 3x minus 12 is less than or equal to 2x minus 4 plus 5. So I'm going to move the 2x to the left. So 3x minus 2x is x. Negative 4 plus 5 is 1, and add the 12, and I get 13. Write that set in interval notation. Okay, so several people did both set builder and interval. So let's do both. There's no like correct way to write the answer, just whatever way the problem you're doing tells you to do it, right? So set builder notation, I would say the set of all x's such that x is bigger than or equal to 13. And if I wanted to do interval notation, I would say, okay, the smallest thing in this set is 13. It goes up to infinity. We include the 13 because it's an or equal to, and we never include infinity. And then if I wanted to graph it, I would have a number line. I'd find 13 on it, and I'd put a square bracket and shade to the right. Three different ways to represent the set of numbers that makes that inequality true. All right, compound inequalities. If I told you that x minus 4 is bigger than negative 6, but smaller than 1, could I write that as one sentence? So x minus 4 is smaller than something, and bigger than something else, right? And just remember that the alligator eats the bigger number, right? So which is bigger, x minus 4 or negative 6? X minus 4 is bigger because the alligator's eating it. So I put a negative 6 here. That's true, right? Negative 6 is smaller than x minus 4. And x minus 4 is smaller than 1. Or equal to. Yeah, so I can write that as just one long string of inequalities. And if I want to solve a compound inequality, do it just like you do an equation, but think of it as having 3 sides. This, instead of like the left side and the right side, now there's like a left, a middle, and a right. And whatever you do to one thing, to one part, you have to do to all 3 parts, with the goal being to isolate x in the middle. So if I have negative 6 less than x minus 4 less than or equal to 1, if I want to isolate x in the middle, what do? Add 4. I'm going to add 4 to all 3 sides of this inequality. Negative 6 plus 4 is negative 2. X minus 4 plus 4 is x. 1 plus 4 is 5. So I have negative 2 less than x less than or equal to 5. That's my solution set. X is between negative 2 and 5. How would I put that in interval notation? Very good. Yes, you always put the smaller number on the left. You always go left to right, smallest to biggest. So it's reflective of the way we draw a number line. Correct. Negative 2 is not in the solution set, but 5 is. Set builder? the set of all x's such that, and then you just put this sandwich. -2 is less than x is less than or equal to 5. Okay, so I'm graphing x minus 4. Y equals x minus 4. It's just a line. I want to know when the y values for this line are between -6 and 1. So I'm going to graph y equals -6, y equals 1, and I'm looking for the y values that are sandwiched between these guys, right? So it's like all right here is where it's this line, x minus 4, is between 1 and -6. What are the x values of this interval? -2 to 4. Sorry, to 5. -2 to 5. And that was what we got algebraically, -2 to 5. So you can solve this graphically by just looking between. Yeah. So you have to do a little bit of like interpretation. Yeah, a little bit of thought to think about, should I include this -2 or not?